Assalamu alaikum, dear students. In today's lecture number 12, we will be discussing one of the bracketing methods, that is the bisection method, and its algorithmic framework. Topics to be discussed in today's lecture are, as I told you that in today's lecture we will be discussing the bisection method and its algorithmic framework. So it will be the first topic to be discussed. Then we will discuss how the bisection method converges, and we'll do its convergence analysis. And finally, we will solve some examples with the help of the bisection method. So let me introduce you to the working of the bisection method. The bisection method is one of the simplest methods to find a zero of a non-linear function. It is also called an interval halving method because in this method you will see that in each iteration the previous interval will be split into two equal parts. To use the bisection method, one needs an initial interval that is known to contain a zero of the function. The method systematically reduces the interval. It does this by dividing the interval into two equal parts, then performs a simple test, and based on the result of the test, half of the interval is thrown away. The procedure is repeated until the desired interval size is obtained. To develop the assumptions for the bisection method, we will be needing the intermediate value theorem. So let me introduce you to the intermediate value theorem in this slide. Let f of x be defined on the closed interval with endpoints a, b. The intermediate value theorem says that if a function is continuous and f of a and f of b have different signs, then the function has at least one zero in the closed interval with endpoints a, b. So if you look at this figure, the function is continuous over the closed interval a, b, and the function has a positive value at point a and it has a negative value at point b. So both the conditions for the intermediate value theorem are satisfied, and if you look at the curve of this function, it intersects the x-axis at this point, which is the zero of this function. Let us see some situations in which the bisection method can be used and some others in which it can't be used. If f of a and f of b have the same sign, either both positive or both negative, then the function may have an even number of real zeros or no real zeros in the closed interval with endpoints a, b. So if you look at this figure, the function has positive sign at both endpoints a and b, and it has 4 real zeros because the curve intersects the x-axis at 4 different points. If you look at the second figure, again the signs at the endpoints, they are positive and there is no real zero for this function. So the bisection method can be applied in such situations. However, if f of a and f of b have different signs, the function has at least one real zero. So if you look at this figure, at point A, the function value is positive, while at point B, the function value is negative, and the curve intersects the x-axis at one point. So the function has one real zero in this case. If you look at the second figure, again the signs at the endpoints, they are opposite, and the function has 3 real zeros in this case. So bisection method can be used to find one of these zeros in such situations. Now we are in a position to state the bisection method. If the function is continuous on the closed interval with endpoints a and b, and f of a and f of b have different signs, bisection method obtains a new interval that is half of the current interval, and the sign of the function at the endpoints of the new interval are opposite. This allows us to repeat the bisection procedure to further reduce the size of the interval to a desirable size. Hence, there are three basic assumptions for the bisection method. The initial closed interval must be given. The function must be continuous on this closed interval, and the function values at the endpoints of this interval must be opposite in sign. If these three conditions are satisfied, then there will exist at least one zero in the interval AB, and the bisection method can be used to obtain a smaller interval that contains the zero of the function. Thus, if the assumptions of the bisection method are satisfied, that is, the function f is continuous on the closed interval AB, and the function values at the endpoints of this interval are opposite in sign, then the algorithmic framework of the bisection method will be as follows. In each iteration of the bisection method, we will find the midpoint of the current interval. Then we will find the function value at this midpoint. If the product of the function values at point A and C, that is negative, then the new interval will be AC. Otherwise, it will be CB. Next, we see graphically how the bisection method goes on. If you look at this figure, the function is continuous over the initial interval A0, B0, and the function values at A0 and B0, they are opposite in sign. So we can find the midpoint A1 of the initial interval A0, B0. Again, the function is continuous in the interval A1, B0, and the function values at A1 and B0, they are opposite in sign. So we can apply the bisection method to this new interval and can find the next midpoint, A2. So whenever the signs at the endpoints of a subinterval are opposite, then that particular subinterval is bisected. As you can see in this figure, that wherever the signs are opposite, then that particular subinterval is bisected. In this slide, the flowchart of the bisection method is given. Let's have a look at it. Given in points AB of the initial interval and stopping tolerance epsilon. If we denote the function value at point A with U and at point B with V, and the function value at the midpoint C with W, then if the product of the function values at point A and at point C is negative, that is UW is negative, then C will become the point B of the new interval. Otherwise, C will become the point A of the new interval. Then, if the stopping tolerance, that is B minus A by 2 less than epsilon, that is satisfied, then we will stop the process. Otherwise, we will find the midpoint of the new subinterval and the procedure will move on. Now let us see some numerical examples of the bisection method. As a first example, can you use bisection method to find a zero of f of x equals x cubed minus 3x plus 1 in the closed interval with endpoints 0, 2? Now, if you look at this function, this is a polynomial of degree 3, so it is definitely continuous on the closed interval 0, 2. Now we will find the function values at the endpoint 0 and 2. The function value at the endpoint 0 is 1, and the function value at endpoint 2 is 3, and their product is 3, which is positive, which means that the second condition of the bisection method is not satisfied. So in this situation, bisection method can't be used. However, if we replace the closed interval in the previous example with 0, 1, then The product of the function values at the endpoints of this new interval is negative now. So in this case, both the conditions of the bisection method are satisfied and we can apply the bisection method in this case.